All right, so I'm going to talk about correlation functions in n equals 4 SYM theory and integrability. So that's the title of my talk. So it's going to be, let me lower it. Okay, so it's going to be correlation functions So I could have started my talk by explaining, for example, what is n equals 4 SYM theory and what are the field contents. But I found it's probably a bit boring. So instead of doing so, in this first lecture, I decided to talk about something more like a general introduction to the integrability. And in particular, I'm going to talk about something like S-matrix bootstrap. So the idea is how to fully determine the S-matrix in certain system by imposing a minimal set of assumptions. Well, it's not minimal because I'm imposing the integrability. I chose this topic because we are in the era of bootstrap. So I think it's kind of interesting to know what are the nice example in which you can actually solve the bootstrap and you can determine the S-matrix. So that's the topic of my first lecture. But okay, so before I start talking about this integrable S-matrix bootstrap, let me start my talk by asking the question, which is, what is integrability? So in finite dimensional system, there is a very well-defined notion of integrability. So in finite dimensional system, essentially the model is integrable, or the system is integrable if the number of degrees of freedom is equal to the number of conserved charges. So for example, one of the example is, of course, harmonic oscillator. Harmonic oscillator, well, which can be multidimensional, and for which the Hamiltonian is something like this. So it's the particle moving in a multidimensional space. And this is, of course, integrable because you can kind of define, well, in this model, you can have like a energy for each direction. So it's clear that the number of conserved charges is equal to the number of degrees of freedom. On the other hand, there are, of course, non-integrable models. For example, if you consider double pendulum, which is something like this. So you have like two sticks attached to each other, and the degrees of freedom is this angle. In this case, the model is not integrable because you only have the energy, which is conserved. So, of course, so this is very clear in quantum mechanics or a finite dimensional system, but things are a bit more complicated if you start talking about, for example, integrable quantum field theory, well, which exists in 1+1 dimension. And the question is difficult, of course, in the quantum field theory, the number of degrees of freedom is infinite. So the naive answer you can give is that maybe the system is integrable if there exists infinitely many conserved charges. Of course, this is not at all rigorous because, like, if you tell it to mathematicians, probably we'll get beaten by the mathematicians because there are many infinite, and like one infinite can be very larger than the other infinite. And in addition to that, it's actually not very useful description of the system, having, well, saying that you have infinitely many conserved charges is not typically very useful in solving the system or in understanding the system. And here, maybe there is actually more practical. It's more like a working definition of integrability, which you might have heard about already. So typically, when you talk about integrable quantum field theory, people talk about the factorized S matrix. Or maybe some of you may also heard about something like unboxed equation. So these are two kinds of things which appear, for example, when you hear the lectures of integrability. And the question is, what is the relation between the two? Because this definition is a natural generalization of the finite dimensional case, but this definition sounds totally different from this definition. But there are actually some relation between the two, and that's what I'm going to talk about next. And in order to see the relation, let's consider the simplest case of non-relativistic scattering. Scattering in 1 plus 1D. By the way, please interrupt me if you have any questions or comments or complaints. So let's consider the non-relativistic scattering. And in particular, let's consider the three-particle 3-to-3 scattering. So you have a three particle coming in, and you have a three particle going out. And the question, but to really define the scattering, so this is P3, what you actually need to do is to consider the wave packet. So this is important in order to understand the understand the relation between the two. So, as in the textbook of quantum field theory, we should really talk about wave packet, so which is given something like this. So you have some Gaussian exponential, and this is much larger than 1. And then you have usual plane wave factor. So this is I. And if you consider the wave packet like this, then in particular, if A is very large, this wave function is peaked around some particular point, and the position of the peak is determined by this equation. Let's call it f of p. Then the position of the peak is determined by this equation. Well, this is just elementary quantum mechanics. And if, in this case, if you solve it, you can easily see that you get x minus m over pi t equals 0. And of course, m over p is the velocity of the particle. So you can actually see this wave packet is peaked around the classical trajectory. So this is, I just explained the basic facts about wave packet and trajectory. And let me now ask, what happens if we assume, maybe I should use this. If we assume that there is infinitely many charges. Sorry, is it?
Do you also allow non-countably infinite charges?
Well, I think about the case where you have like countable infinite charges. And well, that's usually the case in integrability. So I'm going to what I'm going to talk about is not at all a general proof between the two relations, but I'm just going to give you an example in which two facts are related. Okay, so let's consider the charges. So the first charge you can think of is something like this. So if you take the momentum and sum them all, then of course this is conserved always if you consider homogeneous system, because this is just momentum conservation. And also in every system, you can safely assume that pi squared is also conserved because this is energy. So far I'm not imposing any integrability condition. But let's suppose that there is also the generalization of these charges for every possible s, where s is integer, which is larger than 2. So of course this symmetry doesn't exist in general system, but I'm thinking about some particular system where you have infinitely many conserved charges, especially its countable infinity. And let's ask what is the consequences of the physical consequences of these charges. And to understand the physical consequences, the best way is to act these charges to the wave function psi I. Well, let's consider the simple case, and then let's consider just put one charge, so some q of s. So the action of the charges on the wave function is very simple because it's just given by a sum of momenta. So what happens here, so you just need to take a look at here, and this gives you a decomposition of the wave function in terms of momentum eigenstate. And for the momentum eigenstate, of course, these charges act simply. So essentially what you get is originally you have f of p, but now you have something different, which is shifted by alpha s times p to s. And then you can ask, what is the consequence of this shift? So let's start from the case of momentum. And for the momentum, it's very simple. So well, let's consider s equal 1. Then you linearly shift f of p. And if you shift f of p, then of course the trajectory gets shifted as well. But what happens in this case is that trajectory gets shifted by constant. And this constant is the same for all the particles, so which means that actually what you just did is to move this picture on the left or on the right, to the right. And this, of course, is just a manifestation of the translation. And something similar happens also for s equals 2. In the case of s equals 2, you have alpha 2p squared. So you have x minus m over pi plus alpha 2 times alpha 2p. Sorry, so pit pi equals 0. Well, this is a bit ugly. To alpha 2 pi equals 0. And now the shift depends on the momentum, but you can easily see that you can absorb the shift. So you can absorb the shift by the shift of the time. And then it becomes kind of a universal translation of the time, which means that this corresponds to just moving this picture up and down. But something interesting happens for s larger than 2. For s larger than 2, if you do the same analysis, then, of course, what you get is s times alpha s pis minus 1 equals 0. And what's important for me is that this depends crucially on the momentum. So different particles get shifted by different amount. And in particular, if you consider some combination of these charges, if you have the conserved charges like this, then you can actually shift the trajectory by the amount you like. So you can actually separately move the trajectory. So this is actually very profound because what it implies is that if you have some scattering process, then by acting the charges, E2, you can convert this picture to some picture like this. So where the interaction between the two particles happens at very separate points in the space-time. So originally, in this picture, all the particles are interacting in some like a finite region in the space-time, but I just shifted the trajectory so that only two particles meet at one point. And you can also act at different charges and then draw a different picture. Which again is given by a product of two particle processes. So first of all, the fact that this and this are related by the symmetry means that you can actually factorize the S matrix into the two-particle 2-2-2 S matrix. And secondly, because all of them are related by the symmetry, and the symmetry is a symmetry of the system, you can say that this amplitude must be the same as this amplitude. So this is the content, the physical content of the famous unboxed equation. So, well, I should also add that if you impose this symmetry, actually the ingoing and outgoing momenta must be the same, because otherwise there is no way to satisfy the conservation of this QS. So is there any questions so far? Great. Okay. So then the exercise for you, or the homework for you, is to think about the case with a boundary. So if you have a boundary, then you can have interesting process in which particle gets reflected by the boundary. And of course, if you consider general boundary, there is nothing interesting happening. Well, and the reflection is the process of reflection is very, very complicated. But the question is to ask whether there is a nice boundary condition, or actually there is something like integrable boundary condition in which you can actually repeat this argument. And so the question I would like to ask is find integrable boundary condition. And also ask what is the physical consequence. First of all, in this case, you cannot impose all the symmetries that I described here, because first of all, there is no translation symmetry, because you explicitly broke the boundary, the translation symmetry by the boundary condition. So what you need to do is to ask what is the reasonable set of conserved charges that you can impose on this system, and then ask for the physical consequences. And if you successfully solve this problem, then you'll be able to discover the what's called boundary unboxed equation. Okay. Is there any questions so far? Yeah, so Right, you can, yeah. Also here, you can repeat the analysis by using Gaussian wave packet. Sorry, what was the question?
No, the main is that with this S-matrix factorization, other wave packets that are non-Gaussian, which also fulfill this constraint?
Yeah, well, essentially, if you want to have a Gaussian, well, really have a wave packet, you just, what you need to do is to take Gaussian and also set the coefficient of the Gaussian to be very large in order to have a sharp peak. And, well, if you have any wave function, wave packets which have that property, the consequence should be the same. Just have Q3. Okay.
You can still shift the.
Right, yeah, it's actually a bit related to, well, this question, actually.
Also, it seems that having just Q3 might imply
well, having just Q3 probably doesn't allow to like move arbitrary particles. Go ahead.
You wouldn't allow to have a closed time.
Yeah, well, also, yeah, that's actually an important point because here I just wrote the charges as the sum of p to something, but in the real quantum field theory, which is integrable, you should have expressed these charges as kind of local conserved charges. I mean, the integral of the local conserved currents. Well, integral of some conserved currents, and that, yeah, so that gives you additional constraint. Well, actually, it's not always the case that all the system has all the charges for all the S's. There are actually systems with odd S and even S, for example. Okay. So this was the first part of my talk, and then so what I just wanted to show is to show the relation between the charges and the factorizability of the S matrix. And the next question I'm going to ask is whether I can use this kind of factorizability to say something about the S matrix, I mean, especially the exact S matrix. And the example I chose is ON vector model. Well, so what is ON vector model or ON sigma model? So the sigma model is given by this Lagrangian, this path integral. So you have, well, some action which depends on n and sigma, where S of n and sigma is given by the sum of the usual kinetic term plus sigma times n squared minus 1. And essentially, this sigma is just the Lagrange multiplier, and if you integrate it, then you get the constraint that n squared is just 1. And I should also say that this is an n-component vector. And let me first describe classically what is the physics of this model. So classically, as you can easily see, this vector n takes value in s n minus 1, sorry, s n minus 1, so higher dimensional sphere. And classically, so this is the vector in Sn minus 1. And if you expand this Lagrangian by, for example, solving this constraint explicitly, classically you have n minus 1 massless particle, massless fields. And although I don't explain in detail, but there also exists infinitely many charges. You can actually construct infinitely many charges. So it's classically integrable. So there is some formalism which allows you to see that this system has classical infinitely many charges. But, and this n minus 1 massless fields are something like an analog of the Goldstone boson, because this Sn minus 1 is the coset space, which describes this symmetry breaking pattern. But of course, as in quantum mechanically, this shouldn't be the case because we know that in 1 plus 1 dimension, because of the Coleman-Mermin-Wagner theorem, there shouldn't be an exact massless Goldstone bosons. And what happens in this case is that quantum mechanically, you have actually these massless particle gets mass, and in addition, the number of fields becomes n minus 1 to n, and you have n massive particles. So let's try to see that. In the large n limit, because it's the simplest case to analyze. Okay. So let's consider the large n limit. So in the large n limit, you can, large n limit is simple because you can do some analysis by doing the saddle point approximation. So let me explain how this works. So the idea is to first integrate out this field n. And integrating out this field n is basically simple because the action is basically quadratic with respect to this field. And after doing so, what you get is a bunch of determinants because you integrated out Gaussian fields. And what you get is something like this, n minus n. And then you have e to 1 over g squared d to x sigma x, coming from this factor here. So this is what you get. And then the idea is to consider the large n limit in which this g, so you send n to infinity and keeping this combination fixed. And something nice happens in this limit because you can rewrite this action also as follows. So you have d of sigma, and then here you have some effective action for sigma. And this effective action for sigma is trace of log of minus delta square plus sigma minus 1 over lambda times sigma, where lambda here is this combination, which is the analog of 2-Hooft coupling in large and gauge series. And you can clearly see that there is a factor of n in front of exponent which means that in the large N limit, you can do the saddle point approximation. And the saddle point is, of course, easy to compute. So you just need to take the derivative of this guy and set it to 0. So the saddle point equation is something like this. You have 1 over lambda coming out of here equals, what? Equals, so if you express trace in terms of momentum integration, you have something like this, and p square plus sigma over 1. So this is the expression you get after doing the saddle point equation. And this integral can be evaluated explicitly by introducing a UV regularization. And the result is given by 1 over 2 pi log lambda over sigma. Sorry, well, actually, this is lambda over m, where I re-expressed the saddle point value of sigma by m squared. So this is the saddle point equation, which allows you to determine the value of the saddle point, sigma star. And OK, I just erased the original Lagrangian. But if you go back to the original Lagrangian, then you can discover that sigma actually plays the role of the mass for the field n, which means that having non-zero sigma or sigma star in the large N limit means that the particles are massive. And in particular, you can determine the mass in this way. So the mass is given by lambda times, I just inverted this relation. And you can see that there is non-perturbative mass generation. So of course, this is just analysis in the large N limit, but it is believed that it holds also for the finite n. So this is kind of one simple way to see that the classical n-1 massless particles becomes massive particles in the large N limit. Sorry, in the quantum mechanically. So is there any questions so far? OK, good. So now I want to use this knowledge about the spectrum and combine it with the existence of many charges. So I have now n massive particles. So this is just a classical statement, so which I need to erase. OK, so all right. Now, of course, I said that classically there exists infinitely many charges, and that doesn't guarantee that quantum mechanically you also have infinitely many charges. But let's assume that also quantum mechanically there exist infinitely many charges. And as we saw in the first part of the lecture, this implies unboxed equation. So what I'm going to do is to try to determine the S matrix by assuming that the spectrum is given by n massive particles, and the S matrix obeys the unboxed equation. So that's what I'm going to do in the remaining, which minutes? 30? Oh, OK, yeah, you are very generous. OK, I have enough time to do that. OK, yeah, this is terrible. I should do this. But before doing that, this room is a bit too hot. OK, so now I'm ready to talk about the S-matrix bootstrap. And OK, so in particular, I'm going to ask what is the 2-2-2 S-matrix. So what is the general structure of the 2-2-2 S-matrix? So we know that there are n particles, which belongs to the fundamental representation of ON, sorry, the vector representation of ON. So each particle carry one indices. So if you want to consider 2-2-2 S-matrix, then it has 4 indices. And furthermore, because I impose the integrability, I impose the existence of infinitely many charges. So the momentum here should be the same as here. The momentum here should be the same as here. OK. And as Freddie talked about in the morning, so this scattering process is described by the Mandelstam variables, which in this case is given by this expression. And there is also T, which is here. And basically, S describes this process. So you have 2 incoming and 2 outgoing. And T describes this process. And in this case, there is no U, actually, because of the fact, because we are in 1 + 1 dimension. And in addition, this S plus T satisfies the usual relation. Well, essentially, in this case, U is just 0, because we are in 2D. All right, so this is the usual stuff. But to discuss the property, in 2 dimensions, it is particularly useful to parameterize the energy and momentum of this particle by the so-called rapidity variable. So the idea is that we know that all the particles are on shell, and it satisfies this condition. So you can just explicitly solve it. And this basically allows you to translate this piece to one variable theta. So you have theta P1, theta 1, and theta 2. And in terms of this rapidity variables, so let's write it explicitly. This is rapidity variable. And S has a nice form. S is 4m squared cos squared theta 1 minus theta 2 over 2. Well, this is just a rewriting of the momentum, which will be used for later. So in summary, so this S matrix I'm going to talk about has 4 indices, I, J, K, L, and it depends only on the difference of thetas. So this is a general structure. So I often write it just by theta. OK. So before starting to do the bootstrap, let me just tell you the analytic property of this S matrix. This is, again, the standard thing that you can find in the textbook, but I want to tell you about it because I want to translate the analytic usual Mandelstam variable in terms of theta, translate it to theta variables. So in the S variables, we know that the amplitude has branch cut starting from 4m squared, which is the 2-particle threshold. And then it also has the branch cut starting from 0, because there is a cross-end symmetry, and we should expect the branch cut for the T channel. And So this is the complex S-plane. And the physical scattering, so this corresponds to this region. This region corresponds to physical S-channel scattering. Whereas this region corresponds to unphysical S-channel scattering. So what I mean by here is that, okay, if you carefully do the I-epsilon prescription, you actually end up with the above the branch cut, not below the branch cut. And similarly, so here you have T-channel, physical T-channel. And here you have unphysical T-channel. So let me now explain what happens if you map this S variable to theta variable. And in theta variable, things are kind of nice. So let me first draw the picture and explain what it means. So here you have, so in theta variable, this branch cut gets mapped to the branch cut along the real axis, whereas this T-channel branch cut gets mapped to the branch cut along theta equals I epsilon, I pi. And this physical S-channel corresponds to here, and this unphysical S-channel corresponds to here, whereas the physical T-channel corresponds to here, and unphysical one corresponds here. So, well, you just need to use this dictionary to discover what is which region corresponds to which. So essentially, I'm basically opening up this branch cut into a line, into an infinite line. And I did a translation from S to theta because I wanted to talk about the unitarity condition and cross-and symmetry in terms of theta variables. So in S variables, unitarity condition basically means that on the physical S-channel scattering region, you should have, so you have S plus I epsilon, and this amplitude must be 1. Okay, so in general quantum field theory, this should be smaller than 1, but because we are in integrable system, 2-to-2 particle scattering actually is everything. There is no particle production. So that's why I have 1 here. And of course, I can write it more explicitly, like S complex conjugate S plus I epsilon times S plus I epsilon is 1. But because of the property of the S matrix, this object is actually same as S minus I epsilon. Well, this is easy to see. For example, so the property which allows me to do this change is the fact that if you write S matrix as a real part plus IB, then the S matrix here is actually A minus IB. And well, this has relation to the optical theorem. Like if you take the difference, then it should be related to the cross section, which is real and positive value. Okay, so this is a unitarity condition. And if I want to translate, so I said I wanted to translate it to theta variables. And in the theta variables, it becomes a very simple relation, which is essentially S theta times S minus theta is just 1. So this is my unitarity condition. And let me also talk about the crossing. And the crossing is also very simple. So crossing basically means that, okay, now I need to remember that I have indices. So crossing means that if you have S plus I epsilon, then you can also view this object from the T-channel point of view. And in this case, if you go to the T-channel, the indices get swapped, k and j, t minus I epsilon. Well, I think it's kind of obvious by looking at this picture. I have ij going and kl outgoing. But if you go view it from the T-channel, the ingoing particles are I and L, and outgoing are j and k. And I can also translate this to zetas, which gives you this relation. I pi minus zeta. So these are two conditions that the S matrix needs to satisfy. So in addition to these conditions, I want to further impose the unboxed equation. But before imposing the unboxed equation, it's useful to just write the general structure of this S matrix. So the question is, how many parameters this S matrix has? So because of the ON symmetry, what you can write here is some like ON invariant tensors of I, J, K, L. And it's actually very simple to enumerate all of them in this case. So I will write this figure. So this plus 1 over g theta of this, 1 over h of theta of this. And this is I, j, k, l, I, j, k, l, I, j, k, l. Let me explain what I mean by this pictorial notation. So basically, what I mean by this is delta function of ik times delta function of lj. And what I mean by this is delta function of il times delta function of jk. And, well, you can guess what I mean by this also. And of course, because there are 3 different tensor structures, you can multiply any function of theta for each guys. But I just picked one factor as an overall factor. Okay, so this is just the general structure. And now, using this structure, what I'm going to do next is to impose the unboxed equation to see if there is any relation between these S0 and G and H. So let me do that. So now I really need color chalks. So my right hand, so let's impose the unboxed equation. So I first draw the right-hand side of the unboxed equation. So let's consider the case where you have some particle with index red coming in from here, and some other particles with index green coming from here, and some other particles index white is coming from here. And then I also fix the outgoing guys in this way. So I have green here, I have red here, and I have white here. And each crossing is described by one of these structures. And so the question for you is, how many possibilities does this scattering have? Does anyone has a guess? Or maybe you can just give me one. Okay, well, okay, sure, go ahead. Yes, go ahead. Okay, you said one, okay. Yeah, that's true. Okay, so yes, that's true. Because white particle needs to come in from here and go out from here. So there is only one way for the white particle. Well, actually, maybe it might have been better to start with red particle, but essentially, there is only one way. which is basically given by this. Okay? And because we have the unboxed equation, this should be the same as this picture, where you have red particles coming in from here, and green particle coming in from here, and white particle coming in from here, and green particle coming out from here, and the red particle coming out of here, and the white particle is coming out from here. So now the next question is how many structures, how many possibilities does this have? Does this S matrix have? Okay, so let me draw one. So of course I can connect white and white like this. And let's see. I can draw something like this. And then I can also draw something like this, right? But there is actually another one. So I'm basically giving you an answer. So there are actually two structures, well, two possibilities that you can have. So the next possibility is that red is coming like this, and white is again here, and the green is like this, right? And this is the particle 1, so the momentum P1 is coming from, theta 1 is coming from here, theta 2 is coming from here, theta 3 is coming from here. So, and actually, yeah, this is all. So basically, we just need to impose this equation by using this structure. So let's see what we get. So first of all, the first thing to notice is that this equation doesn't give you any constraint on S, because on both sides you have like a SSS and SSS. But it does give you some constraints between G and H. And the constraint, let me try to understand the constraint. So from this picture, so here you have basically just this. So you just have one here. And here you have the scattering between theta 2 and theta 3. And the scattering is like this. So I have 1 over g theta 2 here. And here, again, I have this structure. And the scattering is between theta minus theta 3. Sorry, yeah, I said something wrong. So this is theta 2 minus theta 3 times. And then I have g of theta 1 minus theta 2. Is this correct? Yes. And on the right-hand side, I can do the same. So what is this? So this is the scattering between particle 1 and particle 2. So I have 1 of g theta 1 minus theta 2. And this is just 1. And what is this? This is g of theta 1 minus theta 3. And I can do the same for this guy. So again, let's put theta 1, theta 2, theta 3. So I have g of 1 over g of theta 1 minus theta 3 coming from here. And from here, I have 1 over g theta 2 minus theta 3, if I'm correct. Yes. So this is the equation for g's. So let me try to solve it. Well, of course, you can easily solve it. Well, and if you rewrite this equation, you find that, OK, let me try to rewrite it now. So you have g of theta 1 minus theta 3. And then this, OK, so the idea is to just multiply g, this one times this one times this one. And then you get g of theta 1 minus theta 2 plus g of theta 2 minus theta 3. Do you agree? OK, so all right, so this means that g of theta is actually a linear function of theta. So this is the first conclusion that we got. And So let me try to, OK. So I have 10, 5? OK. All right, so, OK. So then I cannot do the more examples. But OK, so let me then, let's see. Let's see. OK, I'm going to try to finish. OK, so there another constraint is coming from the scattering of this process. And red here. And red here. So if you consider this process and try to solve the equation, again in the same way, you actually find some relation between g theta and now h theta. And the reason why you get h theta is kind of obvious, because if you consider this picture, then there is a process like this in which you really get the contribution from h theta. And essentially, the relation that you get from this is something like this. G of h of theta is g of theta prime plus h of theta plus theta prime. So now I can use the fact that g of theta is a linear function of theta and conclude that h of theta is minus c times theta plus some function d. So this is just, well, sorry, some constant d. And now, so this is what we got from considering two different scattering processes. And now I can combine it with the crossing symmetry, which I just wrote down. And the crossing symmetry does something nice, because essentially the crossing symmetry exchange the index j and l. And if you exchange j and l, then essentially this picture becomes this picture, and this picture becomes this picture. And if you remember it, then essentially if you remember the crossing symmetry equation, then it's actually something like this, if you just forget the indices. So this actually means that g of I pi minus theta must be the same as h of theta. This automatically determines the value of d, and you can actually write h of theta as c times I pi minus theta. So, and the last thing that you need to determine is the value of c. And determining the value of c is a bit more complicated, but you can also determine it by considering a different scattering process, which is basically OK, so let me draw the scattering process. Sorry, not this one. And I have this here, and I have this here. So if you consider this process, and then consider the analogous process in this kind of in this right-hand side of the unboxed equation, then so actually for this process, the unboxed equation becomes this equals bunch of terms on the right-hand side. And if you solve it, then you can determine the matrix structure or the tensor structure of this matrix completely in this way. So you have one overall function of S0 of theta, and you have this minus theta over 2 pi I times delta over theta, and you have this structure. And then you have 2 pi I delta over theta minus I pi times this structure. Okay, and where delta is 1 over n minus 2. So this is where the value n comes in. Okay, so now the rest of the question is how to determine this S0 of theta. But essentially, you can basically determine it by unitarity condition. So unitarity basically leads you to some relation. So you get some norm function here, which comes from the tensor structure. And the crossing basically tells you that I pi minus theta S0 theta is 1. Sorry, sorry. This is not crossing. Crossing equates to S matrix. So by considering unitarity and crossing, you get some function equation for the S0 theta, and then you can try to solve this function equation in such a way that this S matrix doesn't have any poles. Because in the beginning, we assume that there are only n massive particles and there are no other bound states or no other particles. So you need to impose that on the physical sheet, there is no other poles, and you can actually find the solution to this functional equation. And yeah, okay, let me just draw the solution and I will end. So the solution is like this. So S0 theta is Q theta times Q I pi minus theta, where Q of theta is the ratio of gamma function. So in this way, by combining the unboxed equation and the usual analytic properties of the S matrix, you can completely determine the S matrix of this interacting quantum field theory. And in the next lecture, I'm going to explain how this kind of idea can be applied to n equals 4 supermutant theory, which is 4-dimensional supersymmetric gauge theory. Thank you very much.
Any one quick question?
Is this spectrality of this matrix applied for any it's only for the O and sigma model, or?
This is the S matrix for O and sigma model, and well, it's only true for O and sigma model. Is that?
It seems that you only use two conditions, right? One is massive.
Mm-hmm.
The other condition is something like infinity charge, right?
Ah, okay, right, yeah. Okay, so there are other solutions you can write for this, for example, equations, but typically those solutions have extra poles. So if you allow for like extra bound states and so on, there can be other solutions. But I think this is more or less the unique solution if you don't allow the bound states.
Okay. Given the time, we postponed any other question to the discussion session. We now have a coffee break, and we convened at, let's say, 5 minutes past 5 for a discussion session when you can ask Shota and the other lecturers more questions. Let's thank Shota again.